All right, today we're going to start working with the formal definition of a limit. As I've talked about in all of our classes, mathematics, there are definitions that you can always go back to in mathematics that will allow you to explain everything that's occurring in the mathematical world, why we are doing certain things. Okay, there's properties, there's definitions that we can utilize to be able to formulate everything that we have been talking about. Okay, so we're going to go through the actual formal definition of a limit. Once again, we can always go back to this formal definition to be able to solve solutions. Is it used a lot? No, it's not. But the theory behind it is the basis of the idea of what limits are. Whoopsie. It explains the idea of, or utilizes the idea of open dots as we approach, as we get closer and closer to things. As x approaches a specific value, the limit is the value that the function approaches. As x approaches a specific value, the limit is the value the function approaches. What does y get closer to? As x gets closer to something, what does y get closer to? Now, if you go to college and you deal with a lot of theoretical calculus, it depends. It really depends on the college that you go to. It depends on also the person standing in front of you. You have a lot of old school, old guard, they may not be there anymore, but there is an old school, old guard that makes you calculate limits by using this technique for the first couple weeks. There's others that are a little bit more liberal in regards to calculation limits. We'll go through the theory behind it, but you can now use your properties of what we have already dealt with here. So there is theoretical calculus that some people will still go to, and then other people will touch on this sort of like what I'm doing. We'll touch on it and say we have talked about it. But then go back to utilize the idea of limits. You'll be asked to go through this idea in regards to proving what's called a delta and an epsilon to be able to calculate a limit is a value. You'll be asked to do that, but once again, once we get beyond this, we're not going to go back and revisit it. We have a function here, x squared minus 4 over x minus 2. Here is the function that we are dealing with. We want to calculate the limit of this function. Calculate the limit of this function as x approaches the value of 2. Which means we're going to get closer and closer and closer to this value of 2. When we approach a value, we can think of this as we are getting closer to it. We are this open dot away from 2. we have theorized the idea, and we've talked about the idea of open dots. When we have x is greater than the value of 5, we put an open dot on 5 and put a draw line to the right. That's x is greater than the value of 5. Well, what that means is that we get closer and closer to that value of 5, but we never achieve it. We have 5 point an infinite number of zeros than 1. Okay, we are that open dot away from that value of 2 or the value of 5. Well, mathematically, we can explain this and symbolize this with the idea of delta. This is a lowercase delta. We've used the uppercase delta, which is a triangle. The lowercase delta is an 8 minus the upper right hand half circle. This is your delta. It's a distance of value substituted in for x and the values that are approached by x. It's a very small number away from x. So it's a distance between the value substituted in for x and the value approached by x. We dealt with basic ideas of substituting in when we started looking at the idea of limits. This delta that we're talking about here is this value right here. This is your delta. As we subbed in values for x and solved for y, we went to the basic idea of limits. What we were doing is we're substituting in 2 plus delta and 2 minus delta. Because I asked you to sub in 1.9, 1.99, 1.999, 1.99999. So that was 2 minus 0.1, 0.01, 0.001, 0.000001. So we are substituting in values for this delta and seeing what was our y value. As we said, like I said, we subbed in 1.9, 1.99. So we had 2 minus 0.1, 2 minus 0.01. That's that delta value. That is that small value. It's the distance between the value substituted in for x and the value approached by x. Along with this, we have what is called epsilon. Epsilon, which is it's like a curvy E. It's a distance that the limit of a function and the function value for f of x plus delta is a small value from your limit corresponding to this epsilon. So we substitute in this 2 plus delta or 2 minus delta. What we will come up with is we have this value here, which is going to be our limit. When I substitute in my function value of 2 minus delta, we are going to get the value that's going to be our limit minus this epsilon, which would be this value right here. If we substitute it in my function value 2 plus delta, I'm going to come down to this limit plus this epsilon. Which is this distance right here. This epsilon is this distance from my limit to the value I calculated here. So when I substitute in 2 plus delta or 2 minus delta, I'm going to get the actual limit, whatever that value is, plus or minus this epsilon. Once again, epsilon and delta are very small values. They're very small values. Now, what small means is a relative concept. Okay, we're going to go through values today that you're going to sit there and go, that ain't very small. Okay, you get 0.01, that's not very small. Well, that's a relative concept. 0.01 is very small to a million. If I'm a millionaire and I got a penny, here it is. Does that really mean much? No. Okay, so it's a relative concept. So what we are dealing with here is we're taking the limit as x approaches 2 of f. Let's try this. We have x squared minus 4 over x minus 2. So if I take a look at my value that I'm approaching, I am approaching a value of 2. So if I take a look at my delta value here, if x is 0.5, what would be our delta value? What would be our delta value? How far are we away from the value of 2? 0.5. And we're towards the negative side of that, so we should probably throw in a negative 0.5. If I'm at 1.75, how far am I away from 2? What's negative 0.25? Negative 0.1, negative 0.01, negative 0.001. And likewise, if I go 2.5, I'm just going the positive side to this. So we have 0.5, 0.25, 0.1, 0.01, 0.001. With this, we can find function values. So if I would click the clack in my calculator, into my y1, I have x squared, my quantity of x minus 4, x squared minus 4, divided by quantity of x minus 2. And I find function values of 1.5, 1.75, 1.9, 1.99. I want to find my function values. Then 2.5, 2.25. What is our function values? Go ahead and read down your column. What do you have here?
3.5, 3.75, 3.9, 3.99, 3.999, 4.5, 4.25, 4.1, 4.01, 4.001.
Now, if we took a look at our limit here of our function, if I tried to plug in my value 2, I would come down to 0 over 0. Can't do it. But if I factor, we have a discontinuity that we can remove. So we can factor, cancel, and then sub in. We get the value of 4. So if we take a look at our epsilon here, our epsilon is our distance that we are away from our limit. We would come down to the exact same thing we did with our deltas. So we'd have negative 0.5, negative 0.725, negative 0.1, negative 0.01, negative 0.001, positive 0.5, 0.25, 0.1, 0.01, 0.001. That's how far we are away from our limit of a value of 4. Well, once again, as we talked about in your calculator, if you would go to find the value of your function at the value of 2, does your calculator give you a value? What is our function value at 2? Do we get a value? No, we don't get a value there. So once again, this is this limit. So at this value of 2 on our calculator, if you take a look at your graph of your function on the paper, I don't know if you can see it or not, but you have a little space in there at the value of 2. What we can throw in there would be an open dot. Well, how close can we get to 2? Well, we're an open dot away from 2. How close then are we away from our limit? We're that open dot away from our actual limit. So we have an open dot at this order pair 2 and 4, where really what we are at here is we're 2 plus or minus delta, and our function value is 4 plus or minus this epsilon. So when you're dealing with limits, once again, looking at the limits, we have 2 plus or minus delta and 4 plus or minus epsilon. Where they're, once again, that open dot away from it. That f of x be defined on an open interval x naught, except for possibly an x naught. Okay, we're not defined there. Okay, that's the idea of limit as x approaches x naught. Where we may or may not be defined. The limit as x approaches a of a function is a number L. Okay, so this is as x approaches a of a function is a number L. Is a value. For every number epsilon greater than the value of 0, there exists a corresponding delta greater than the value of 0, such that for all x, zero is going to be less than this x minus this x naught, which is going to be less than this value of delta. When I subtract these two values here, I'm going to be between 0 and delta. How big is delta?
Please excuse this interruption at this time. Sophomores with the last name beginning N through Z. If you need a retake picture taken, or if you have not had your picture taken this year, please report to the auxiliary gym at this time to have that done. Thank you.
If I subtract this x naught minus x, the value that we're approaching, and the value that we're plugging in, we're going to be somewhere between 0 and delta. Once again, delta is a small number. If I take the function value at that value that I substitute in, minus the limit, and subtract them, I'm going to be smaller than the value of epsilon. Okay, so if I subtract the two x values, I'm going to be between 0 and delta. If I subtract the limit from my function value, then I'm substituting in, I'm going to be smaller than the value of epsilon. We're going to run out of time. We will stop there today. We have nothing for tonight then. We will continue with this tomorrow.